Welcome to Toddcast number 35. We're continuing on the addition to alkene reaction section. And so let's do a reiterate pickup. Last time we talked about just the generic reaction where you have a pi bond, you have two carbons in that pi bond, and you add an H to one side and either an OH or a halogen to the other. That was our sojourn into this reaction. Then mentioned that you can potentially add two H's or two halogens. You get syn and anti-addition. Barely touched on it. That's going to be elaborated on down the road. But the thing left you with was the concept of Markovnikov addition, the regioselectivity question of does it add to the more crowded or less crowded side, and what it is. So the first atom to attach, if that is your it adds to the less crowded side, and the bulkier group gets defaulted into the more crowded side. That's called Markovnikov addition. It's a regioselective phenomenon. And then briefly touched on this concept of stereoselectivity, where if it adds to one side or the other, you can potentially get an R chiral center or an S chiral center and create stereochemistry. And so we're going to continue on that same path and just go into it in more detail. So for symmetric alkenes, we generally don't have an issue of regioselectivity because they're symmetric. Either side's going to generally yield the same thing. So for instance, if I have a double bond between carbons 3 and 4 of a 6-carbon chain. So in this case, I'm using 3 hexene, so carbon 1, 2, 3, 4, 5, 6. So hex, and then 1, 2, 3, double bonds between 3 and 4, so we call it 3 hexene. Because on each of the carbons of the double bond, I have an ethyl chain and an H, an ethyl chain and an H. And syn and trans or cis, E or Z for the original double bond will matter eventually if I have an asymmetric center. But when it's symmetric, we luck out. We don't necessarily come up with any restrictive stereochemistry issues of doing one side over the other. So it'll make more sense of that in a second. But this H can go on, let's say, the left one. Br ends up on the right. So I end up with this Br here. Or the H can go on the right and the Br can go on here. Because they're equally substituted, H doesn't have a preference. One H or one H. It's going to go to either side. So if the H goes left, the Br goes right. If the H goes right, the Br goes left. But it ends up, this is 1, 2, 3 bromo, 4, 5, 6 hexane. This is 1, 2, 3 bromo, 4, 5, 6 hexane. So they're both 3 bromo hexane. Now, I'm going to ignore the stereochems question for now, just worry about regio. But we do end up with a chiral center here. And because this is sp2, the H goes on and doesn't make a chiral center, who cares? But the Br is going to go onto a carbocation, wherever the carbocation is. A carbocation is planar, so Br can attack from on bottom or on top, which means it can generate either the R or the S, depending on which way the Br goes. I'm ignoring that for now and just considering the regioselectivity. So in this case, we get the same compound, so it's kind of a moot point. Asymmetric alkenes, so let's stay in that simple example. We're dealing with hexene, but now instead of hexene being 3, it's now 2 hexene. So for this particular case, I'm going to start with the double bond. So just double check 1, 2, 3, 4, 5, 6. So I have 6 atoms, so it's hex, but now it's 2 hexene. And lower one is 1, 2, 3, 4, 5, 6. So again, 6, so it's hexene, but 1 hexene and 2 hexene. Now it is asymmetric. So it's still substituted with 1H and an R group, 1H and an R group on this case. So the preference of one side or the other for the H isn't as clear, but a methyl versus a propyl group means the two sides of the carbons are unequal in the end. So when I do that, I'm going to add, let's say, if the H went on to 3, Br went on to 2, you get 2 bromohexane. And if the H in turn went on 2 and the Br went on 3, you have 3 bromohexane. So it just got a little more complex. There is no preference. H goes where H is, 1H here, 1H there. H go to either side, so you're going to get a mess. You're going to get a mixture of 2 structural isomers, 2 constitutional isomers. Sorry about that. So 2 bromohexane and 3 bromohexane. Okay, so we're looking good with this. Stereochemistry is also still going to be an issue because you have a chiral center here and a chiral center here. So I'll just go ahead and make note of that. We're ignoring it for the time being. We'll definitely make a big deal about chiral centers eventually. But the regioselectivity is random. It really should be close to 50-50. Now, H might have a little bit easier time getting in on this side than this side because methyl is smaller than propyl. So you might end up getting possibly a little more H here. So this might form in like a 52 to 48, depending on temperature distribution. And I'm just totally making up numbers. Just more than 50 and less than 50 was the key thing on that one. But it would be trivial to decide between those two. For this one, however, it now becomes more distinct because the H, if it goes on less crowded, it's distinctly less crowded here. There's two H's at the terminal end. There's one at this carbon. So the H goes here, you end up with three H's here in 2-bromohexane. But if the H goes to the more crowded side, or to the more crowded side, Br goes here, H is going in an unfavorable way. So the 1-bromo results from a less favorable addition. H wants to go where H is, so two H's at the end, one H here. So it goes to the less crowded side. So H wants to go to the end, forcing Br on 2. So this should be your major product. This will be your minor. Definitely not a close to 50-50. This one is going to be distinct, depending on temperature, it could be 80-20, 85-15, something like that, but a definite preference for so-called Markovnikov addition. So again, I'll write that word, and we're going to make a much bigger deal about it in this. Markovnikov. I'm so sorry. Just having a spelling blank right here. But that word will pop up. That's going to be huge. So first chemist to observe this, determine H goes where H is. So let's get on with that. So competing mechanisms, want to consider what's going to happen. So when it is this terminal one, so we're going to look at that one in a little more depth. This time it's 1, 2, 3, 4, 5, 6, 7. So instead of hexene, it's now heptene. So be it, it's 7 instead of 6. Same basic idea. H goes where H is. So H could go to the first carbon, or H could potentially go to the second carbon. So if it were to go out, we're going to pick up the H, Br. So notice the mechanisms look the same. I curve the arrow slightly different here and here, ever so minimally, but this is to imply it's going this way, leaving this is a positive, this implying going this way, leaving that as a positive. It's just real minor difference, but I just want to emphasize that the electrons come from the middle of the pi bond, but because they're curving this way, it's like swinging open that way or swinging open that way. So H goes on to carbon 1 in this mechanism. So you get a plus on carbon number 2. And H goes on to carbon number 2 in this one, you get a plus on carbon number 1. So second factor is just come into play. The first factor was kinetics, steric hindrance. H goes where H is, H goes where it's less crowded. Two H's here, H in a large group. H goes on less crowded seat is why it chose this. But then the secondary benefit, this carbocation right here is on a secondary carbon rather than a primary. Here, it's on a primary. Secondary carbocations are more stable than primary carbocations. So for two reasons now, one, it adds to the less crowded side, so less steric hindrance when it goes on. And two, a more stable carbocation intermediate results from this. This is your more stable intermediate. This is your more probable pathway. So your two competing mechanisms, Markovnikov and what we're going to call anti-Markovnikov, are both transpiring together. Once a Br comes in, the Br is going to go to wherever the plus is. So Br is going to go to carbon 2 on this one, carbon 1 on this one. When it does, you'll end up having this come down. And here's your final product. The more substituted, the 2-bromo, and the less substituted 1-bromo. Major product, minor product, because it went through the more stable intermediate and had the lower energy transition state to begin with. The higher energy transition state because it's a little less crowded, or a little more crowded here, excuse me, and less stable intermediate. So the unfavorable pathway and favorable pathway leads to the more substituted product, the more stable product. And this pathway, the less favorable one, actually leads to the less substituted, less favorable product. So major product, minor product. So major, minor. Important to distinguish that early on. So within a week, Just gonna expect you to just recognize that. That's gonna be a secondary thought, just something you just automatically know. So Markovnikov, there it is, I don't have to spell it. All 11 letters. And again, want to quote the immortal Forrest Gump in saying H goes where H is, so that we know H is going to go on at the site with the most H's already on the molecule. So in this case right here, we have the left carbon being less crowded, the right carbon being more crowded. So H is going to end up on the less crowded carbon. But we can also use this quote to say H is on here, no H's are on here. So 1 H versus no H's. 0 is less, 1 is more. So H goes where H is. There's more H's on this carbon than this carbon, so the H is going to end up on that carbon right there. So H goes on first, so it chooses the quote-unquote better seat, as we mentioned earlier. So these electrons will come out and pick up that H, kicking that pair of electrons over to chloride. So H chooses the less crowded or better seat. And then chloride goes on second, so it gets stuck in the worst seat, the leftover seat, the one right here. What I have is a carbocation. I should put that in a moment. And I should also make note, I've been lazy in my drawing so that it comes in prettier. These should both be planar because sp2, but it's as soon as the Cl goes on, plus charge is gone, and these do go down. And as I mentioned earlier, I probably should draw it as anti-addition because it's not a chiral center on either case. I'm sort of ignoring it for now, but I should start getting in better habits. But Markovnikov addition follows the Forrest Gump principle. H goes where H is. Hopefully you can do that. So let's go ahead and play the, can you identify whether it was Markovnikov or anti-Markovnikov? So I'm adding H3O plus, which is basically H plus in water. So the same thing we did before, we add H2SO4 and water to an alkene. We ended up adding a hydration reaction. So added water across a double bond. Let's count 1 H here, no H's here. So that means when I added it, H went here and OH went here. So H went to the carbon that had more, was Markovnikov. Okay, let's do another one. So I'm going to ignore just this massive group of reagents here and just focus on what's going on here. No H's and 1 H. So we've done this comparison before. 0 H and 1 H, seems like the same old thing. If OH is going here, that means H went here. So H here, OH here. So H is on this carbon, the one with more. H went where there were more. So it was Markovnikov. Okay, so I guess it's just always Markovnikov. This is nice and simple, I think. So here we have this. H on peroxides. So I'm not sure what peroxide does, but let's see. No H's, 2 H's. So that's definite distinction. So here's my 2 H's. So if Br went here, oh shoot, H went here. Oh no, this is opposite. H went here and Br went here. So in looking at this, H is actually going with their less H's, which means it's actually not Markovnikov. It's known as anti-Markovnikov. So this set of reagents then, you might make note of this. Apparently when I use peroxide in there, the rules change. We'll learn why down the road, but it essentially comes down to this. The peroxide takes the H, so the H is no longer going to go on here. The peroxide got it, so it's now the Br that's left over. So the Br is the first one to go when you do it in peroxide. Br is going to choose the better seat, and H gets stuck in the worst seat. So there's a mechanistic reason for it. So it's still a case where the first thing on chooses the better seat. But when I use acid, apparently H is the first thing on. When I use mercury, acetate, mercury is the first thing on, but that eventually is going to be replaced by an H. And so we have these different pathways we use, but it's still always going to be the first thing on chooses the better seat, second thing on chooses, or doesn't choose, it defaults into the worst seat. Okay, so let's see what happens here. pH3, THF, H2O2, ooh, that's a peroxide. Somewhere in the back of my mind, from a previous experience, such as this question, I know peroxides do something. So I'm going to pay extra careful attention. Let's see, 1 H here, 2 H's here, so I count it. OH is on the N carbon, so OH went where there were 2 H's, meaning H went where there's only 1, so H went to where there were less H's. anti-Markovnikov, which doesn't surprise me because I saw the peroxide. So apparently when peroxide is involved, typically you're going to get anti-Markovnikov. So again, we'll go into that more in detail on mechanisms in the future. But just really want to emphasize this concept of regioselectivity. You have two carbons to choose from, one that's more crowded, one's less crowded, one has more H's, one has less H's. H goes where H is, or first thing on goes to the less crowded seat, the one with H's is less crowded. Either way you want to look at it, Markovnikov is where that happens, defaulting the bigger group to the more crowded site. Markovnikov, Markovnikov, anti-Markovnikov, anti-Markovnikov. Okay. So here's basically how it's going to work. When we use pure hydrogen halide, HX, no peroxide, nothing else. So it's using addition reactions to an alkene, it will follow Markovnikov rules. It's only when you mess with it and add some peroxide in there. But in general, HX is going to add in a straightforward fashion. So H, the first thing on, no H is one H, less crowded, so H is going to go here. So H is going to add here, plus charge will be there. For this one, H is going to go to less crowded, leaving a plus charge in the middle. Last one, H is going to go to the less crowded, so two R groups, one R group and an H, so less crowded here. H is going to go here, leaving a plus charge on the more crowded site. Okay, so I have these three distinct intermediates. Now it's a matter of just the Br coming in there, the Cl coming in there, and the Br coming in there. So second step, the fast step, the halogen, or halide, I should say, adding, is pretty straightforward. But notice the theme here. The H went to the less crowded site, the one with more H's, and we ended up with a tertiary carbocation, a tertiary carbocation, and a tertiary carbocation. Those are the most stable versions we get, aside from, let's say, resonance stabilized. But for straight alkyl carbocations, tertiary beats secondary, secondary beats primary. So this is pretty straightforward. It's not a challenging concept. Again, it's a new concept, so it takes practice. Make sure you do plenty of homework within the book. So regioselectivity, we'll say, is not done. We're just done with that initial look at it. Now we're just going to pound it out through examples. The other thing mentioned was stereoselectivity. Which side does it add to? So if I were to draw this out, my double bond will have a pi, a segment of pi. So let's emphasize the pi. I shade on bottom simply because that's just how I decided to draw it. No, there's no rhyme or reason for how it works. Okay, so there's my p orbital. I have attached to this carbon, I have, and then on the other side, I have H. So something like that. So that would mean when the H goes on, doesn't matter where the H goes on, it's symmetric. But what does matter is once it goes on, I now have, so let's say I choose to put the H on the right. And then let me draw it in red to emphasize it's a new one. So I now have a plus charge here. This still has an empty p orbital. An empty p orbital can be attacked by Br minus this Br minus can come in from the bottom, or it can come in from the top and go either side. If it comes in from top, we'll push these two groups down. If it comes from bottom, push these two groups up, which means my chirality is going to change because I have an ethyl, an H, and a propyl group. So I can have three different things attached, either in a way where it's S chirality or R chirality. So Br is going to be top priority. This is second, this is third. So if it comes in from top, it'd be clockwise in R. Comes in from bottom, it'd be counterclockwise in S. So your chirality, your stereocenter becomes key. Okay, I'm erasing all of this. I'm going to let the pictures do it. So 3, 2, 1, clear. Not that you couldn't just play back the video and see it. But an achiral reactant is going to get a racemic mixture. You're going to get an R and an S. So again, this one is my R when attacked from on top. This is my S when it attacked from on bottom. You get a 50-50 mixture, so it stays racemic, or it stays optically inactive, I should say, because it's racemic. So you can't suddenly gain chirality. You can go from 0 to a non-zero number only if you have a catalyst that has some chirality. But if everything in solution starts optically inactive, no catalyst, no enzyme, just adding an achiral molecule, you can never get optoactivity. You'll get a racemic mixture under those conditions. This, however, has 1, 2 chiral centers, so consequently, this definitely has chirality, so it is not alpha d equal to 0, which means we now have the chance, the potential to get optoactivity. And so we do that by having something that is not racemic or not enantiomers at all, just diastereomers. Okay, again, H is going to go to the less crowded site, which is here, which forces the Br to go here. When it does, again, we have a planar carbocation. So let me go ahead and draw the best I can here. If I get rid of this bond here, we put the H on first. And this right here is my empty p orbital. Br is free to come in from the back or in front. If it comes in front, it's going to bump into this group and potentially this group over here. So it's not as favorable. And if it comes in back, it can avoid those two bulky groups in front and may actually have an easier time. So this is sp2 hybridized, so it's planar, so it doesn't matter here. But this other side, the interference of these two sticking in front, make the backside attack more favorable, meaning we will get a major and a minor. This coming in from the backside with less steric hindrance, less stuff to run into, is going to be my major product. This one is going to be my minor product. So major, because it's easier to come in from behind. Minor, because it's harder to come in from in front. So major, minor. I should just let my beautiful drawings do it. The front led to the minor, and the back led to the major. So this is so-called stereoselectivity. This is really hard to grasp at first. So hang in there, bear with it. But anytime you have an sp2 center, an empty p orbital, or a pi bond, you have the freedom to attack from top or bottom, from below the pi system, from below the p orbital, or above the pi system, above the p orbital. And so you can always attack from top or bottom, which means you can get one chiral center in one way, the other chiral center in a different direction. This is known as stereoselectivity because we're ultimately choosing top or bottom to decide what stereoisomer will form. This is going to be just an ongoing question. We're going to see this repeatedly. Markovnikov questioning, regioselectivity, and stereoselectivity. So you're always going to ask two questions on any reaction. Does it choose one carbon over the other? Is there a preference for one carbon over the other when we do the addition, regioselectivity? And does it attack one at a time or two at a time? Meaning if it attacks one at a time, one thing goes on, and it creates a situation where the second thing can go top or bottom. If they had two at a time, there's going to be some mechanisms where both of the things out at the same time. They can only go syn. They can only go from the same side, which is a different sort of stereochemistry. Okay, hopefully this is going well. It's starting to get in that territory where you're going to have to really think about this, spend more time. So before, a lot of the concepts were review from GChem, and honestly, fairly simplistic thoughts. Now we're getting into a much more complicated just whole scenario. So going to end the recording. Have an absolutely wonderful day, and we'll talk soon.